Hi everybody, I'm Miss Peachy from WCA Earth Science class, and today I am going to walk you through how to do the um, lab measuring orbital speed of planets. So this one is the last one on your calendar for the school year. And then we'll be in summer, so that's pretty awesome. Um, for this particular portfolio, there is a student information guide that goes along with the gizmo, but I don't like it very much. Looking at the student information guide, it's just a little different from what you're actually measuring here. So I'm going to say just follow what I tell you to do rather than looking at the student information guide. So I'm going to move me over just a little bit here. And you can see here, this is the actual gizmo. Now when I'm in the lesson viewer, that'll be the second link. Okay, you do want to open the top link because that's going to give you this document right here, Measuring Orbital Speed, Earth Science. That's what you need. This is what you're going to turn in to me. So you can just click and, type and fill this stuff in here as far as the data table and everything as well. Okay, so once you've done that, then here is the actual viewer here. And it won't look like this initially. It'll look just like this. Okay, so it's going to be kind of zoomed out. You'll see just the first 4 planets, the terrestrial planets, Mercury, Venus, Earth, and Mars. And in order to find out more information on those planets, you need to click on additional data. There's a drop-down box here where you can select any one of the 8 planets or Pluto, which is the dwarf planet. Used to be 9th planet in the solar system. And then I think I like to look at the orbital paths as well. It just gives me a little bit of a visual of where they're moving. So the first thing you're going to do is you are going to get some data on these particular planets. So starting with Mercury, I'm going to click on additional data, and it's going to give me a lot of information about Mercury. Okay. What I'm going to do is I'm going to do some calculations. So the first thing it says, mean orbital radius in AU. Now AU is the distance from the Earth to the Sun. So it's a measurement we use to compare in a lot of, at the scale of the solar system, because that's a very large distance. It's roughly 93 million miles. So that's the number we're going to use to represent a single AU. And we're looking at just the radius. Now radius is going to be each path around is roughly a circle. It's not exactly a circle. It's actually a little bit more of a very circular ellipse. So it's slightly elliptical. But we're going to pretend it's a circle for now. The math we're going to use is going to be involving maths of a circle. Okay? So the radius is 0.387. So I'm going to go ahead and put that in my data table right here. Now, I made some changes at the top of this data table just to help you out right now. So don't worry about the fact that these is yellow, blue, and green, and you don't have those colors. I've made some changes here to help make this a little easier to understand. And you can copy those changes if you'd like, or just use this screen to help you as you're completing the portfolio. So 0.387. The second thing says circumference of the orbit, and this is a calculation. You're going to take 2 times pi times radius. Now, most of your calculators will have a pi button on the calculator. If you're using your phone as a calculator, what you need to do is you need to make sure that the lock screen, this is just an iPhone, so it's not going to be the same as Android, but you can actually have the pi button will show up on here as well. Otherwise, if that's not the case, if you don't have a calculator that has pi on it, use 3.14 instead. Okay, so you can take the radius, which is 0.387, times 3.14 times 2. 2 times pi times r. And when I did that, I got 2.43. And again, that's astronomical units. So it's about a little less than 2.5 times the distance from the Earth to the Sun. So then that's that piece of information. So by the way, I also have numbered these columns for you just to make it easier to see, when I'm talking about what to do. So the first column with the names is column 1. Column 2 is the mean orbital radius. Column 3 is the circumference. Column 4 is period Earth in years, or period in Earth years, excuse me. Column 5 is the orbital speed, and column 6 is orbital speed in miles per hour. Okay, so I numbered the columns just so that we can communicate a little better through this tutorial. So the next thing I'm going to do is look at the period in Earth years, and that's going to be found on the gizmo itself. So I look down, and period in Earth years is 0.24. So it takes a little bit less than a quarter of a year to go once around the sun for Mercury. It's closer, so that makes sense, right? So I put that in here. And now I'm going to figure out orbital speed in AU per year. To do that, I take column 3, divide by column 4. Yellow or blue and yellow make green. That was my logic for the color choices here. So 2.43 divided by 0.24 is equal to 10.1 AU per year. Okay? Once you have this, you're going to take this number here, multiply by 93 million, and divide by 8,760. So 93 million is the distance for 1 AU. Whatever 10.1 times 93 million equals, and get that value, and then divide that value by 8,760, which is the number of hours in a year. Okay, and that gives you about 107,226 miles per hour. So that's Mercury's speed. So as Mercury is careening through the universe, or through the solar system here, it's really fast. That's a fast speed, much faster than anything on Earth can travel. So that is the speed. You're going to repeat this process for the rest of the planets, including Pluto, the dwarf planet. So basically, column 2 and columns 4 here are stuff you get from the gizmo. And then columns 3 and 5 and 6 are calculations based on those. Okay, so fill in that data table completely. And then you're going to look at this. How does the increase in orbital radius affect orbital speed? In other words, as the radius gets bigger, do we see a relationship? Does speed go up or down? Is the planet moving faster or slower? Is there a relationship? And if so, what is it? Is it going to be a direct relationship, in which case as the orbit or the radius gets bigger, speed gets bigger? Or is it an inverse relationship? As the radius gets bigger, speed goes down. Okay, so kind of tell me that. And then you're going to want to look at the gizmo itself, and you can observe the planets in orbit just by pushing play here. You kind of see what's going on. Okay, and it kind of gives you an idea for that last question as well, even without the calculations, And as we zoom out to observe the outer solar system, you even get a better idea. So I'm going to speed this up a little bit here. Kind of gives you even better idea. And I'm not going to say anything because I want you to come to your own conclusion there, okay? So all you're going to turn in to me is this worksheet, which has your data table with calculations and the drawing conclusion questions. You do not need to do the extension, it says. So we don't need to do this. I'm going to just say no on all of that, okay? Save it. Make sure you save it, guys, and then submit that to the Dropbox. If you have any questions or concerns, feel free to give me a call at extension 2204, or you may send me a webmail message. Have a great day, everybody.